Right. So let's move on with our chapter 2. Okay. Right. Exclusive or this is where we stop last lecture. So what is that? We learned what have we learned? Basic gate, AND gate, NOR gate, AND gate, OR gate, NAND gate, NOR gate, and NOT gate. And this exclusive OR. So this OR gate, exclusive OR gate, is defined with 2 input, 1 output. So the output is high when 1, and the only one input is high. Output is low when both inputs are equal. So basically, is when these 2 inputs are different, either 0, 1 or 1, 0, the output is high. When these 2 inputs are the same, the output is low, exclusive. So these 2 inputs have to be different. The symbol of the XOR gate is looks like an OR gate with double curve on the input. This is how we draw it. And the Boolean expression we have a round, so a circle. Within that circle, we have a flat sign. So this is the symbol we use to represent the XOR gate. And the truth table, as a definition, we have 4 combinations for the 2 inputs. And then when they are the same, either they are both 0 or they are both 1. We have 0 as output. When they are different, exclusive, when the 2 inputs are exclusive, that means when A is 0, B is 1, or when A is 1, B is 0, the output is 1. So that's the exclusive OR gate. Exclusive NOR gate is the exclusive OR gate plus the NOT gate. So that's simply just to revert the output. When the XOR gate is high, the NOR gate should be that output inverted. So that's a bubble added at the end of this XOR gate. A bubble means an inverter, a NOT gate. It's just a simple version of this triangle with a bubble. Okay. So that's so this Boolean representation. We have this overbar. You know, this overbar is a NOT gate, NOT, and this overbar can be extended very long. So this is X. So this is A X or B overbar. That means we get the XOR gate first. On top of it, we have an overbar. That means after the XOR gate, we have an inverter. Okay. So let's see exclusive NOR gate. And the truth table is the result of the XOR gate inverted. Okay, very simple there. Then, so gate equivalence. Now we have to look at, after we learn all these basic gates, can we find the equivalence among these gates? So can we use one gate to replace another gate? Or can we use a number of different gates to represent the other type of gates? So a NAND gate can be represented by an AND gate with the inverter output. This is very simple. We will see it. And a NAND gate can be represented by an OR gate with the inverted input. What does that mean? So this is what we can do with it, all the variety that we get. So a NAND gate on the left here is equivalent to this OR gate with two inverted input. So why this is so why do we need to know this? And that's because at the very beginning, when we don't have configurable device, we have a basic gate. We're allowed to use these basic gates on the chips that's available. So when we get an electronic device, a chip that has many, for example, 10 or 20 same gates, we want to have our design with both AND gate or OR gate. But with the chip, it only provides us with one type of gate. So we have to be able to convert that into another type of gate. So that's why we learn this conversion. Nowadays, FPGA gives us the flexibility of doing this without having to physically do the conversion manually ourselves. But we have to know how it is done. Okay, so these two are equivalent, and for NOR gate, a NOR gate can be represented by an OR gate with the inverted output. That's simple. It also can be represented by an AND gate with inverted input. Okay, so, and we call this the DeMorgan's theorem. So these two types of conversion between different types of gate, we call it DeMorgan's theorem. So it should be very simple once we learn the rules about this conversion. So this is a NAND gate. So the dot represents AND. You can delete this dot simply like A, B, that also represents AND. So A and B are inverter, so that's a NAND gate. It's equivalent to A naught. So that's A over bar, that's the inverter of A, or B naught. So these two input, A and B, they are inverted. Then the inverted input get all together, then put on so the total output will be the output of that OR gate. So these two are equivalent. Similarly, we have A or B. So this is a NOR gate. So A or B inverter. So it's a NOR gate. It is equivalent to two inverter. So the two input are inverted first. Then they are put into the two input of this AND gate. So that is the same as using the NAND gate. We call these two combine these two lines together. We call it DeMorgan's theorem. How to remember that? So very easy rules for us all to remember that is to break the bar and change the sign. So what do we mean by that? We break the bar, the long bar that is the inverter. So this is NAND. We break that and then change the sign. The sign now is the AND sign. We want to change it to an OR. So the bar is broken and the sign is changed. Same thing, the second line, we break the bar and then change the sign. So we break the bar, now we have two inverter. Then the sign is changed from OR to AND. So this is how to remember it. So you will never forget this DeMorgan's theorem. Okay, so this is what we just said. So two common errors. So what we don't do for this is that the previous slides, that's the correct way of breaking the bar and change the sign. So these two, they are not the same. Why this is wrong? Because now we see it's this for the first line, the bar is broken, but the sign is not changed. So a NAND gate is not equal to two inverted inputs and together. So this is wrong. Similarly, we have the NOR gate. We break the line, but we didn't change the sign. So this is also wrong. So these are two common errors. So 2 steps, break the line and then change the sign. Don't just do 1 step